Example 6.1, an 18-gauge copper wire, the size usually used by lamp cords, has a diameter of 1.02 millimeters. This wire carries a constant current of 1.67 amps to a 200-watt lamp. The density of the free electrons is 8.5 times 10 to the 28 electrons per meter cubed. Calculate the magnitudes of the current density and the drift velocity. This example is used to differentiate between current and current density. In addition, we also want to calculate the drift speed of an electron in a copper wire. So let's start by calculating the current density. So A is about current density. So the first thing that we want to do is that we want to set up an image. So we start by setting up an image of the current. So I see a cylinder. And when I'm looking at the cylinder, I know that there's a cross-sectional area, which is A. And then if I'm having a copper wire, we'll color it yellow. And now we have to talk about the concentration first. So when I'm looking at the concentration, I'm imagining that I have a cylinder within the copper wire. So you could see that this is at one end right here, and then this is the other end. So when I'm looking at this, what I'm finding here is that we have a lot of electrons. And according to the concentration, this right here, this number tells us that this concentration of electrons is then going to be on the order of n of 8.5 times 10 to the 28 electrons per meter cubed. Now, note that's huge, but that's for a meter cube. For a wire, it's got to be smaller. So now that we have that, I'm going to have current that's now coming through this area right here, this cross-sectional area. And so all we know is that these charges, on average, have a drift velocity that's moving in that direction. Now, when I look at this current here, they're telling us that this current has a value of 1.67 amps. So these charges, as we've just shown, are spanning out a little cylinder with some concentration, and they tell us that the area A of an 18 gauge wire is, so it's got to be A of 18 gauge wire. The cross-sectional is of course a circle, and then they gave us the diameter, not the radius, so then this has to be 1/2 times the diameter that they gave. And if we compute this area, we get 8.17 times 10 to the -7 meters squared. And that's a tiny area, right? So if I was to think about the picture that we're actually seeing here, I have this area. And as I have this area, I know that the area right here is this 8.2 times 10 to the -7 meters squared. It is tiny, tiny, tiny. But I have that amount of current passing through this little tiny area, which is 1.67 amps. But that's what's going on. The current density is a different animal. The current density tells us is how much current is spread out over a unit area of 1 meter squared. So if you look at this and you make a comparison, look at the comparison between this, right? That's 10 million times, right? That's roughly 10 million times or 1,000,000 times bigger of area that we're looking at the current. So if I was to take 1.67 amps, and then I go into that, it's that current's going to be ginormous. It's got to be the orders of millions of amps per meter squared. So now if we start to look at the pictures, here's what we're really looking at. So picture-wise, I imagine that I have a little copper wire. And here's my copper wire right here. And what do I know? I know I'm going to get a current of 1.67 amps. Right, but so this area here is tiny. And of course, we don't care about the length, but that diameter is very, very, very tiny. Now, if I look at the current density, we're talking about a ginormous area where the current is crossing. So in other words, I'm comparing this area into that little tiny wire area. So when I look at the current density coming in, this current, that guy is just going to be on the order of 1,000,000 amps. So this guy is huge. And so when I start to calculate this number, right, we know that we got to calculate this number. It's then going to just be the current divided by the area, but that's a tiny area, of course. And so we're going to see here that now the current density, which is the current divided by the area, is then going to be 8.17 times 10 to the minus 7 meters squared divided into 1.67 amps. So to 3 sig figs, you could see here that we're the order of 1,000,000 amps per meter squared, and that's the current density. So once again, yes, this number is ginormous, but it has a standard unit area, whereas the copper wire does not. So let's summarize this thing. In comparing the current to the current density, it is true that they have different units, but they're still effectively the same thing. And so we said, so if we're comparing them, the first thing is that a current through the wire is 1.67 amps passing through a tiny area of 8.2 times 10 to the minus 7 meters squared. So this is specific to the wire. On the other hand, a current through a wire with area 1 meter squared is 2.04 million amps. But it's still the same number. This is still 1.67 amps. But now you have to talk about the whole area of that. But this has proper units, if I could say that, proper units of meters squared. So, once again, this implies 2 million amps per meter squared. Once again, but they mean the same thing because the current density is just a standard quantity that we can look at. Now let's talk about the drift. Oops, spelled that incorrectly. The drift speed. It's more common to say drift velocity, but the velocity indicates that you have to put in a direction, but we can't put in a direction. From the definition of the current density, the drift speed is then going to be, so this is the current density, and it's directly proportional to the velocity. So that just tells us then that the drift velocity is then going to be the current density divided by NE. So if I start putting in these ginormous numbers or tiny numbers, I'm going to get the concentration times the charge of the electron, which is tiny. And then we go into the current density, which is large, which then gives us a value of 1.5 times 10 to the minus 4 meters per second, or 0.15 millimeters per second. And this is the drift velocity. This is probably the main reason for doing this example. Look at that drift velocity. It's 0.15 milliseconds. Millimeters per second. This drift speed of the electrons, this drift speed of electrons in wires is extremely slow at 0.15 millimeters per second. It is so slow. So to put this into perspective, this drift speed is considerably much slower than the rate of honey being poured out from a container on a cold day. It is incomprehensible how slow that value is. So here's the catch. Even though the electron's speed in copper is extremely large. Remember how large? Well, it's at a million meters per second, which is about 2 million miles per hour. I think it's like 600 miles per second. So even though the electron speed in copper is extremely large, the frantic collisions with the metal ions cause an extremely sluggish forward motion at 0.15 millimeters per second. So if you were to just look at the ratio here, right? So this is electron speeds in metal to the actual drift speed. And what we find here, that this is going to be the order of 1,000,000, and this is going to be of the order of 10 to the negative 4, which means that's on the order of 10 to the 10. So that means here that the speed of the electron is reduced by a factor of 10 billionth of its original speed without collisions. We will talk more about this conceptually in the next lecture.